Hello everyone, a very good evening, one and all of you. I hope I'm audible and visible. So let's wait for 5 to 10 minutes so that everyone can able to join this session.
Good evening, ma'am.
And good evening.
మా మేడం కొడుతుంది నిన్ను మా మేడం కొడుతుంది నిన్ను
Okay, Keith, you can ask till now.
Shall I ask, ma'am?
Yeah, you can ask.
Madam, regarding question number 6 and 7, ma'am.
Question number 6 and from my assignment question.
Assignment 10, madam. Assignment 10.
No, that have been given to you in NPTL or from my session.
No, NPTL, madam.
Okay.
Actually, the key given is they have written only visual, ma'am. I have written visual learning. And seventh question answer is project based. I have written project based learning. Further, they have not given the marks.
Oh, okay.
One
So
second.
actually, I didn't have seen that the questions. So you can share that question here, or we will see it later. Otherwise, if you can share that question. Otherwise, just ping me that question. I will take both that questions.
Madam, I am saving the question as image format, madam. But in the
Okay.
chart, I am unable to paste the same, ma'am. How do I share the question to you?
Okay, okay. I will see that question. Uh, Actually, I am checking that question only.
Yeah,
Six and
question number
seven.
6 and 7, ma'am. Same data given for both the questions.
Okay, okay, yeah. So what you have answered and
No, stop sharing. Okay,
no, you are able to share your
yeah,
screen.
I'll stop sharing, madam. Stop sharing.
No, 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 no. You can share. You can.
I can share. Okay, okay.
Yeah.
Let me check. Then we should open this. అదే 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 ఇద్దరికి వెళ్ళి షేర్ తెలుసు ఆప్షన్
So you are saying that your answer
yeah
is correct.
question have you seen the I have shared madam no question
Yeah, yeah, yeah.
yeah question number 6 I have answered visual learning strategy
Okay,
group A I have answered madam but in the
okay,
key given by the NPTEL was only visual
okay. Yeah. So you have written what visual learning strategy.
yeah yes ma'am
So here it is a mistake only here because they have given visual group A or visual or practice based. So you
yes
have
ma'am
to answer like visual only. Top three neighbors. Like only one answer. I mean you have to write visual, not a visual learning strategy. That's why it is
what is the
taking.
difference between visual and visual learning madam
See, it is given, but it is in the answer. In the options, they have given only visual or practice based, not a learning strategy.
but there are no multiple choice right
Yeah, no multiple choice, but you have to just fill whatever given to you in the question, whatever I mean sentence or word given to you. So you
okay
can just write an email to them also. Okay, my answer is correct. Just I have written visual learning strategy besides of visual, but my answer is correct, right?
yes madam
So you can ask them because your answer is correct, right?
yeah yes
Because
ma'am
you
that's what
learning strategy you have written, that's why they have incorrected it.
yeah yeah see if it's a human
Mm,
is correcting
yes,
he
only
or she will be
visual.
correct ma'am.
Yeah, if you have written only visual, then it will the correct answer.
Yeah, that's what. How can it be wrong, ma'am? That is what
Yeah,
my.
it's not
I
a
lost
wrong.
two answers, ma'am. Sixth and seventh also. Seventh also
Oh,
I've answered correctly. Practice-based learning I have written.
oh, acha, you have added the learning because you
Yeah,
have to
learning. I
answer
have
on.
added the word learning because there is it's a learning studies, right?
Yeah, yeah, that's fine. It's I mean common, but in the answer, I mean in the that table itself, you can see that strategy
Yeah,
they
yeah.
have given visual or practice based. You have just added the extra word. I don't know why they have. Actually, it is a automatic, na all those things. So whatever
What, ma'am?
answers
I'm
they
very
have,
much shocked and worried also.
yeah. So you have just got a correct answers, but just you have added that extra words, that's why you have got incorrect. So you can write them an email by my answers are correct, I have just derived it correctly, but because of that learning strategy or practice based learning you have just added that one, that's why you got a incorrect. So let's see whether they will consider or not.
Thank you so much, ma'am.
Yeah, yeah. So you
Shall I
can,
stop?
yeah, yeah, you can stop. Okay, so are you able to see my screen right now?
Yes, ma'am. We are able to see.
Okay, just stop your presentation just
Yeah,
once.
yeah. Yes, ma'am.
Yeah. So, hello everyone. Let's start the session. So, my name is Pooja Verma. I'm PMRF Research Scholar from IIT Kharagpur, and instructor for this course is Professor Jayanta Mukhopadhyay, Department of Computer Science and Engineering, IIT Kharagpur. This is the week 11 live and interactive session on computer vision. So, this is the week content for this week, that is dimensionality reduction and sparse representation. So, I hope all of you have gone this week video lecture. So let's solve some numerical which will be very similar to your assignment problems. Okay, so let's see our first question. Our first question is, consider a 3D data point in the 2D space, that is -1, that is this data point, and then 0, 0, then again this data point, and 1, 1, this data point, as shown in the figure below. So which of the following will be the principal components for this data? So any one of you have any idea how to solve this question or this type of question? How to find out the principal components from the given data? Okay, so let's solve this question. So the given data points is -1, 0, 0, and 1, 1. So the principal components are the eigenvectors of the covariance matrix of the zero mean data. Okay, so first what we are doing to compute the principal component, first we have to compute the mean from the given data. Okay, so first step is compute mean, that is mu, that is the mu x, mu y from the given data. Given data. So our given data is -1, 0, 0, and 1, 1. So first we will compute for the x. This one first, this one. So our first one is -1 plus 0 and plus 1 divided by 3. Right? So here -1 plus 1 will cancel out. So 0. So overall result you will get 0 here. Similarly for mu y also, because that have same data, -1 plus 0 plus 1 divided by 3. Again you will get the value 0. So mu you are getting 0, 0, right? So now we have to find out the centered data matrix XC, right? Or to compute the principal component, first you know that we have to compute the covariance matrix, right? We need to compute the covariance matrix to find out the principal components. and writing as PCs. Okay. So how we can just calculate it? So already we know that the formula you can represent it as, or this symbol is also represented by the covariance matrix. So you can write it 1 by n summation of xi minus mu and xi minus mu transpose. We are calculating like this one. So here we have got the mu 0, right? So summation xi means there are three data points. So n is equal to 3 here. So here n varies from 0 to n minus 1. Already we know that. So any xi. So here our mu is 0, right? So you will get xi into xi transpose, right? Here summation xi into xi transpose. So xi is our data. So our center data you will get. Let's say it is center data is represented this one xc. Okay. So we can just, if you do the all the summation, so here we can write it like this also 1 by n minus 1 xc and xc transpose, where xc is the this one xi minus mu. Okay, this is, so here our mu is 0, so we can write it like this. Now first let's compute the covariance matrix first. Okay, so here our n is 3, mu we have just calculated. So you can take first, our first data is minus 1, right? So you can take like this one also, -1 and -1, then just take a matrix and compute it. Or other way is, so just compute all the x's, xc1, or you can say xi, then just add all the matrices. And other way, you can just calculate it, the covariance matrix for this 2D space data. You can just, I told you 1 minus 1, n minus 1, xc into xc transpose, right? Already I told you in the previous slide. So we can just write all the data points here into the, this is a related to xc, then take it xc transpose also. Okay, so here our n is 3, so 3 minus 1 you will get here, and then this xc, and then take a transpose of this one, right? So -1, 0, 1, here again -1, 0, 1, right? You can calculate in another way also. Just take one data point, just take a calculate the matrix and add all those matrices. Okay, you can do that way also. So it is a little bit easier and faster way. So that's why I have taken this way. Okay. So here, if you just multiply row into first row into column, then this row, so you will get 2 cross 2 matrix, right? So here -1 into -1, you will get 1, 0 into 0 plus 0, 1 into 1 plus 1, right? Similarly, for this one also, 1 plus 0 plus 1. Similarly, for the second row, first column, 1 plus 0 plus 1. And similarly, this in second row, second column. So 1 plus 0 plus 1. Okay. So now here you will get all the matrices 0.222. If you just further just divide it in, so you will get 1, 1, 1 and 1. Right? Now to compute the eigenvalues and eigenvector, what we are doing, that is calculated by a characteristic equations, right? To find eigenvalues, that is lambda, by solving characteristic equation. So what is our characteristic equation? That is S minus lambda I is equal to 0, right? So here S that we have calculated is all the 1, 1, 1 and 1 minus lambda I, you know that identity matrix. So 1, 0, 0, 1, right, is equal to 0. So further, if you just solve it, you will get 1 minus lambda, here, here 1, here again 1, and again here you will get 1 minus lambda, right? So now we have to calculate the value of the lambda, that is eigenvalues, right? So just directly we can calculate it. 1 minus lambda square minus 1 is equal to 0, right? So here if you further solve it, uh, ex expand it, so you will get here 1, right? 1 square plus lambda square, that is a minus b whole square, right? A square plus a square minus 2ab. Similarly, so minus 2 lambda minus 1 is equal to 0. So here the plus 1 minus 1 will be cancelled out. Here you will get lambda square minus 2 lambda is equal to 0. If you take lambda common, so here you will get lambda minus 2 is equal to 0. So what the different lambda values you will get? Lambda 1 comma 2 is equal to 2 comma 0, or you can say that lambda 1 is equal to 2, lambda 2 is equal to 0, right? Now find out the next, we need to find out the eigenvectors, right? So here 2 first eigenvector value
Madam,
is
excuse
2.
madam.
Yes, yes.
Uh, how you have taken the sequence 2 comma 0, madam? Why can't it be 0 comma 2?
0 comma 2 you can take it.
We can
Here
also
2
take.
values, you can take it.
It's okay, madam. Thank
Okay, so here first we are taking, you can solve for lambda 0 also, but 0 is a minimum value or lesser number. So we are taking 2 because it is a non-zero value. Okay, so if we are putting it here, so it will all the, if we take lambda is equal to 0 first, so this will be 0, so you will get the this matrix itself. Okay, so from that one you can also calculate. So let's first find the eigenvectors. So for okay, let me take my slide. Okay, so let's find out the eigenvectors. Eigenvectors for that eigenvector is represented by V. Okay, let's say for lambda is equal to 2 or lambda 1 you can take. So already we know that the characteristic equation S minus 2i, I'm just putting the lambda value in that equation. Okay, or you can you must be studied into your previous classes, that is how to find out the eigenvalue and eigenvectors. So this is the formula. So S minus 2i into this eigenvector values is equal to 0, right? So just put all the values 1, 1, 1, 1 minus again 2i. So directly we can write 2, 0, 0, 2, right? We can write it like this into V, or you can say that where we can write S V is equal to lambda I also, that is, has been solved into V is equal to 0. So just if we take the minus into this one, so here you will get the matrix is 1 minus 2, you will get minus 1, 1, 1, minus 1, right? Here and into V equal to 0, right? Now we have to calculate the values for the eigenvectors. So we also, we can, it is a 2D space, so we can take v1 v2 also. So just from the place of v you can take v1 and v2. So if you further solve it, you will get minus v1 plus v2 is equal to 0. Again v1 minus v2 is equal to 0. From both equations, actually you will get v1 is equal to v2, and from here also v1 is equal to v2. So the both equations are same, or the both values are the same, v1 is equal to v2. So we need to normalize the eigenvector, that is v, what we will get, it will be any constant number to define, right? So both values are same, it can be any value, 1, either 1, 2, 2, any value, right? It can be for both, but that will be the equal
Yes,
values.
ma'am.
So to normalize this one, so let's say it is taking k because k will vary 1 to n, right? And that can be any number. So to normalize this one, right? So we need to take a magnitude of these two. So here you will get k square plus k square for both is equal to 1. So if you solve it, 2k square is equal to 1. Here you will get k is equal to 1 by root 2. Just solving any value we can take. Okay. So our first principle, so the first principal component, it can be any other values also if you solve any other way. Okay. So the first principal component, let's say I'm saying it, is V1. So it will be the same value 1 by root 2, 1 by root 2 for both V1, V2 for both value. And our second principal component V2 must be a orthogonal to V1. So already you have studied in the PCA. So two principal components must be orthogonal to each other. Okay. So the second principal component must be orthogonal to V1, right? So an orthogonal vector is can be any value. So what is the orthogonal vector? Anyone have any idea? That dot product must be
When we
equal
multiply, it should be equal to
equal to
0.
yeah, that must be multiplied and equal to 0. Okay. So what are the orthogonal other orthogonal vectors with corresponding to this one? So can you find out? So an orthogonal. So you need to find out what are the other orthogonal vectors corresponding to. We have got that one principal component, and next we need to find out the next what are the orthogonal components with respect to these values. Okay, 2 1 by root 2 into 1 by root 2. So it can be a minus 1 by root 2 into 1 by root 2. This one, or first one is positive 1 by root 2 into minus 1 by root 2. That can be a other possibility. These are the orthogonal to this one, right? So I'm just removing it from here. So let's check whether it will be the orthogonal, or if it is after multiplication you will get the same values or not. So in the question, so here it is the different values are given. So one principal components we have got, but it is not a 1 by root 2, 1 by root 2. Now we need to check from which options you will get the value of 1 by root 2 and 1 by root 2, or minus 1 by root 2, 1 by root 2, or vice versa. Okay. So our first option is 1 by root 3 into 1 by root 3. So this one is incorrect. Our next option is root 2 divided by 2 into root 2 divided by 2. In this option, if we multiply in the numerator as well as denominator by root 2, so you will get the value, so 2 by root 2 into root 2, here 2 root 2, right? So overall you will get 2 into 2 root 2, and here also you will get 2 root 2. So if you just, so you will get 1 by root 2 1 by root 2. So option B, first principal components we are matching, right? Now let's check for other options. Here it is a multiple options correct in this question. So that's why we are just checking. Our next option is option C, that is minus root 2 divided by 2 in root 2 divided by 2. Similarly, in this one also, just multiply and divide by root 2. So 2 root 2, and here also root 2 into root 2. Here you will get 2 root 2. So here you will get minus 2 divided by 2 root 2. Here again 2 root 2. So here again it will be cancelled. You are getting minus 1 by root 2 into 1 by root 2. Okay. So this one is a orthogonal to our first one, right? So B and C are the correct answer in this question, because after this normalization you will get here again 1 by root 2 into 1 by root 2, and here that it's orthogonal. Second component will be 1 minus 1 by root 2 and 1 by root 2. These options are the incorrect because it is not matching. Here the option A is 1 by root 3. 1 by root 3, it is not matching with our options, and similarly option D also. Okay, so option B and C are the correct answer for our this question. Okay, so have you understand this question? Anyone of you have any doubt? Is it okay for you? Okay, so can we move to the next question? Okay, so I'm just moving on to our next question. So our next question is, if data points, that is again the same data point, -1, -1, 0, and 1, 1, are projected into a 1D subspace by the dominant principal component, what are their coordinates in the projected 1D subspace? So any idea how to solve this question? Okay, so it is related to the first question itself. So already we have calculated the eigenvector, that is 1 by root 2, comma 1 by root 2. Okay, already the same data points that is given, that is -1, 0, 0, and 1, 1. Okay, so in the previous question we have calculated the eigenvector, that is 1 by root 2 and 1 by root 2. So to calculate the next projected 1D subspace, so just a minute, can you just stop the working? Okay. So the first they have asked, are the projected into a 1D subspace by a dominant principal component. So what is our dominant principal component? So the dominant principal component, dominant principal component is the unit vector. Okay, so that we have calculated in the our previous question, question number 1. So that we have got 1 by root 2 or 1 by root 2. Okay, so the coordinates in the projected 1D subspace are found by the projecting the centered data point, that is these are the xi's, onto the dominant principal component V1. So the new coordinates that is called ZI, the new coordinate ZI is equal to XI dot product of V1, okay, with the dominant principal component. Okay, so the projected 1D subspace can be found by projecting the center data point that is Xi onto the dominant principal component V1. Okay, so this one is a dot product of these two. Okay, so our Xi's are already here it is given minus 1, 0, 0, and 1, 1. So first we will find out for x1 that is minus 1, minus 1. So minus 1 and minus 1. So z1 we will get that is z1. So it is a x1 dot product of v1. Okay. So our x1 is minus 1 and v1 is 1 by root 2 and 1 by root 2. So just if you calculate it, we will get minus 1 dot product 1 by root 2 plus minus 1 into 1 by root 2. And here overall you will get minus 1 by root 2 minus 1 by root 2. So overall you will get minus 2 by root 2. If you further solve it, you will get overall minus of root 2, right? Similarly, we need to find out the Z2, Z3 also with respect to other xi. So our x2 is 0, 0, right? So Z2 will be x2 dot product with v1. So here you will get 0, 0 and with dot product of 1 by root 2 and 1 by root 2. So overall here you will get 0 plus 0. So overall you will get 0 here, right? Similarly for x3 as well. So here it is a 1 and 1. Here I can write for x2. So z3 we will get x3 dot product with v1. So here 1, 1 and 1 by root 2, 1 by root 2. So here again we will get 1 by root 2 plus 1 by root 2. So here we will get 2 by root 2. Overall you will get root 2. Right? Right? So the coordinates in the projected 1D space are the coordinates are I'm just writing that is first one minus root 2, second one is 0 and third one is root 2. Okay, so these are the new projected 1D subspace coordinate minus root 2, 0 and root 2. So just check which option minus root 2 option A is the best matching. So option A is the correct answer for this question. Okay. So have you understand this question? How to find out the new projected 1D subspace coordinates? Okay, so I hope all of you have understand this question. So now moving to our next question. Our next question is consider the data points that is 532, 460 and 253. Now compute the covariance matrix of the set using PCA. So now we need to find out the covariance matrix using PCA from the given data points. So any one of you can just at least answer for this question how to calculate the covariance matrix on this PCA. Already we have solved the first question, but there 2D space is given, here 3D data points are there. Okay, in the same way, we have to calculate it. Okay, so here three data points are given. So three data points are given. That means a three-dimensional data. Here n is equal to 3, right? So that means d is also 3. That means three dimension. Now first from the given data points we need to compute the mu. That is mean of the each data point. Okay. So for each data point we first calculate the mu. That is mu x, mu y, and mu z. Let's say. So here the all the three data points are given. So first directly I'm calculating the all mu's. So first each first place is mu x, second place is mu y, and third place is mu z. Okay. So 5 plus 4 plus 2 divided by 3, right? And the second one is 3 plus 6 plus 5 divided by 3. Similarly for the third one also 2 plus 0 plus 3 divided by 3. Okay, so here just you add all those values. So 11 by 3 here, 14 by 3, and here 5 by 3. So if you further just divide it, you will get the values of 3.67. Here you will get 4.67, and here you will get 1.67. Is it right? Are you calculating these values? Okay. So already in the previous slide also, first question, we have solved a zero mean data centric matrix that is called SXC data matrix, that is XC is. So it is calculated already told you the covariance matrix is calculated by S 1 by n summation I is equal to 0 to the n xi minus mu and xi minus mu transpose, right? So first we will find out all the xi minus mu values, that is x1 I is 1 2 3, right? So for x1 x2 and x3 as well. So x1 minus mu already we have calculated. So our x1 is this data point 532, right? So 5 minus 3.67. Our next value is 3 minus next mean is 4.67, and our next value is 2 minus 1.67, right? So if you just subtract it, you will get the value of 1.33 here. Here you will get minus 1.67, and here you will get 0.33. Similarly, we have to calculate for x2 minus mu and x3 minus mu as well. So I'm just taking the another slide to calculate all these values. So our next value is x2 minus mu, right? So our next value is 4, 6 and 0. Okay. So 4 minus 3.67, 6 minus 4.67, and our next value is 0 minus 1.67. So here you will get the values 0.33, 1.33 and minus 1.67. 1.67. That is x2 minus mu value. Similarly, x3 minus mu we have to calculate also. So next data point is 2, 5 and 3. So 2 minus 3.67. Similarly, 5 minus 4.67 and 3 minus 1.67. So from here you will get minus 1.67 and here you will get 0.33 and here you will get 1.33. Okay, so all the xi minus mu values we have calculated. Now next we need to calculate the x transpose with the just matrix of these two. So first one we will calculate x1 minus mu and x1 minus mu transpose, right, for the covariance matrix. Then we will add all these matrices because it is a 3 cross 3 matrix, so we can't directly calculate. So we have to calculate in this way. Okay. So our first value that we have got, that is 1.33 minus 1.67 and 0.33. Okay, and its transpose, that is 1.33 minus 1.67 and 0.33. So if you just multiply the first one with this row, again the second row with this all these values and this one, so you will get 3 the costing. So if you just multiply 1.33 into 1.33, what value you will get? Any one of you have any idea? Can you calculate these values? 1.33 multiplied by 1.33, similarly 1.33 multiplied by minus 1.67, 1.33 into 0.33. So if you just multiply these values, then these values, so you will get this type of matrix: 1.76 minus 2.2211, and here you will get 0.4389. Okay, here again you will get minus 2.2211. Here you will get 2.7889, and here you will get 0.5511. Again in the next row you will get 0.4389 minus 0.5511, and here you will get 0.1089. Okay. Similarly, if you just multiply x2 minus mu and x2 minus mu transpose, so our x2 minus mu is 0.33, 1.33 and minus 1.67, and its transpose 0.33, 1.33 and minus 1.67. So again we have to multiply in the same way. So you will get here 0.1089, 0.4389, and here minus 0.5511, and here you will get 0.4389, 1.76 minus 2.2211. Okay, in the third row we will get minus 0.5511 minus 2.2211, and here we will get 2.7889. Okay, similarly we have to calculate for the x3 minus mu and x3 minus mu transpose. X3 minus mu and x3 minus mu transpose. So our x3 minus mu value that we have calculated is minus 1.67, 0.33, 1.33. Just remember all the steps and just you have to make sure your calculation must be a correct. Okay, otherwise you will get a wrong answer also. Minus 1.67, 0.33 and 1.33. So overall matrix you will get if you just multiply. Here you will get 2.7889 minus 0.5511 and here you will get minus 2.2211. Here you will get minus 0.5511, 0.1089 and 0.4389 here. Here you will get again minus 2.2211 and here you will get 0.4389 and 1.76. Okay, so all the transpose and the things you have calculated. Now finally we have to calculate the covariance matrix, that is 1 by n and summation of all the xi minus mu and xi minus mu transpose. So just we have to add all these values. So the this is three-dimensional and n is equal to 3 and just add, if you add all these matrices, three matrices that we have got, this one and this one and this one, just we have to add all the three matrices. Okay, if you add all the three matrices, the value that you will get, that is 4.6578 minus 2.333. Here you will get minus 2.3333 again 2 minus 2.33, 4.6578. Here you will get, and here again minus 2.33, and here again you will get, if you just add these values, and 4.6578. Only diagonal matrix you will get a different values, that is that will also all diagonal values are same and other off diagonal values are the same if you just add it. And if further divide the 1 by 3 all these values, so you will get here 1.5526. Here you will get minus 0.777, again minus 0.777. Here again these values are the fixed. Again here you will get 1.5526 minus 0.77 and minus 0.77, 1.5526. So this is our final covariance metric. Okay, so these are the steps already we have solved. So from here, if you just check, so you will get the this answer. No, option C. Sorry, not a B. Option C is the correct answer for this question. Okay, this is a procedure of compute the covariance metric. Okay, so have you understand this question? So I hope all of you have
Yes,
understand this.
madam.
Okay, so now moving to our next question. So our next question is a data set is centered at the origin, that is mu is given as 0, 0. The first principal component, that is a projection vector, is v1 0.6 and 0.8. If the data point is x is equal to 5 minus 5, what is the projected coordinate z1 in the 1D subspace? Again, this is the same type of question that we have solved in question number 2. So already we know that the projected coordinate z1 is found by the dot product of the data point x and unit principal component unit principal vector v1. So here v1 is also given, data point xi is also given. That is data point x is 5 minus 5 and unit component principal component vector is 0.6 and 0.8. So z1 is calculated as x into v1, right? So here x is given 5 minus 5 and v1 is given 0.6 and 0.8. So directly you can calculate it 0.6 into 5 plus 0.8 into minus 5. Okay, so if you just multiply here, you will get 3.0 and here it is a minus, so here 4.0. Overall value you will get minus 1.0 or you can say minus 1. Okay, so from here you can directly see that option A is the correct answer for this question. Okay, okay, so now moving to our next question. So our next question is, consider a dictionary in 2D space consisting following atoms 1 1 minus 1 0, sorry, minus 1 1 and 1 minus 1. For the given vector 2 3, evaluate its representation using two atoms of the above dictionary following orthogonal matching pursuit OMP. Okay, so here given data vector to represent is, this is 2 3, let's say it is a y, and dictionary atom, that is D, it is given as 1 1 minus 1 1 1 minus 1. Okay, so let's solve this question. So any idea how to solve this question? Okay, so given data vector to represent, let's say it is a y is 2 3, that is it is given. Okay, and a dictionary atom, in this case dictionary atoms, that D, it is also given D1, D2 and D3. What are our dictionary atoms? That is D1, here 1, 1, here D2 is minus 1, 1 and D3 is 1 minus 1, right? So we need to represent this Y as a linear combination of two atoms using OMP, right? We need to represent Y as a linear combination of two atoms using OMP, that is orthogonal matching pursuit. So the first atom, let's say D1, is one of the most correlated with Y, this one, because all the values are positive. Okay, so first we are taking this atom. Okay, so the first atom, that is D1, is the one most correlated. That's why we are taking it with Y. So to compute the first, we use the normalized dictionary. Okay, with Y. So to compute the further correlations, we will use the normalized dictionary. We will use the normalized dictionary. So first we will calculate the normalized dictionary. How we will calculate it? That is T1, and it is calculated by root of 1 square plus root, because all the values are 1. So here you will get root 2. Similarly for the D2 also, second attempt. So again 1 square plus 1 square, sorry, here minus 1 square plus 1, so again root 2. For all the values you will get 1 square plus minus of 1 square, again root 2 you will get. So next we need to calculate the correlations. So how we calculate correlations using the OMP, orthogonal matching pursuit. So the formula is to calculate the correlation. Let's say it is Ci because there are 3 atoms. So for each, so it is calculated by di transpose y mod of, and in the normalization of di's. So first we will calculate for C1. So that is D1 transpose y. So here mod of D1 transpose y, because first we are calculating for C1, and normalization of D1. So our first data point D1 is 1 1, right? And D1 is 1 1, for your reference I'm writing, and y is 2 3, and normalization D1 is calculated in root 2, right? So just put, it is a dot product of D1 transpose y. So just 1 into 2 plus 1 into 3, and in the denominator you will get root 2. Okay, so C1 you will get 5 mod of 5 divided by root 2. So it is again 5 by root 2. So just further you calculate the values, you will get 3.53. Okay. Similarly, you have to calculate for C2 again. So here you will get D2 transpose Y and normalize of D2. So again our D2 value is, I think, minus 1 1, and D3 is 1 minus 1. Okay, for reference I'm just writing these values. So first is minus 1 into 2 plus 1 into 3 divided by root 2. Okay, so here you will get minus 2 plus 3 divided by root 2. Here it is a normalization, not this one. So here you will get 1 by root 2. Again you will get 0.707. C3, if you calculate, so you will get D2 D3 transpose Y, and in the denominator normalization of the 3 values. So here you will get again 1 into 2 plus minus 1 into 3, and in the denominator root 2. So here you will get 2 minus 3 divided by root 2, right? So here minus 1 in the mod. So overall, if you just, you will get 1 by root 2 itself, 0.707. Okay. So all the correlation we have calculated. So here our next target is the maximum correlation is with D1, lambda 1 must be 1. Okay. So the first selected atom is D1. So the maximum correlation is with D1 lambda 1 is equal to 1. So the first selected atom, here we are selecting selected atom is D1 and D1 is 1 1, right? So our next target is to calculate the two atoms of the above dictionary from the OMP. So next we need to calculate the residuals. So how we can calculate? So the residual is calculated by next step. Just I'm writing two, that's why here. So the is residual is calculated by, that is represented by R1, let's say, and it is y minus P1 y. Okay, and here where P1 is projection on D1, projection onto D1. Okay, for OMP, that is orthogonal matching pursuit, for that we are finding out these values. The residuals is found by the projecting y onto the space spanned by the selected atom, that is selected atom is D1 our first. So for the first step, that is the same as the projection onto the first atom. Okay, so the projection onto the first atom, onto the first atom, first we will calculate for alpha 1. Okay, so alpha 1 is calculated by, this is a formula, that is the same d1 transpose y here, and y already we know that the 2 3, and mod of normalization of d1 square here. Okay, so I'm calculating alpha 1 values to the in the next step, next slide. So alpha 1 is d1 transpose y, and here normalization of d1 square. Okay, so d1 is 1 1 and y is 2 3, right? So 1 is a 1 into 2 plus again 1 into dot product, and d1 that we have calculated root 2 normalization whole square, right? So here if you just 5 divided by root 2 square, we will get 2 only. So alpha 1 we will get 2.5 here. Okay. So alpha 1 value we have got. Now we need to calculate the R1. Okay, just put in that equation R1. So R1 is equal to, here again, y minus alpha 1 d1. Okay, alpha 1 d1. So y already we know that this is a value 2 3, and alpha 1 that we have calculated 2.5, and d1 already we know that 1 1. So from here we will calculate 2, here is 3, 2 3 minus 2.5 and 2.5. So here you will get here again minus 0.5 and 0.5. Okay. So now the selected atom, that is DJ D1, that maximizes correlation with the residual R1. The remaining atom is first atom D1 we have selected. Okay. For that we have calculated the correlation that maximizes the residual R1. Now the next remaining, for the next remaining atoms, that Okay, so I'm writing here now. Select the atom DJ, that can be a 2 or 3. Any other also that maximizes correlation with residual R1 from the remaining atoms. Remaining atoms. So our remaining atoms are D2 and D3, right? D1 we have selected first. So for the next D2 and D3, we need to find out the correlation again. Okay. So let's say it is a C2. The next correlation, the correlation formula already told you. So we are calculating for D2 first, then D3 also. D2 transpose R1 and normalization of D2. Okay. So our D2 value is -1 and 1, right? So -1 and R1 is minus 0.5 plus 1 into 0.5. Again, it is we have calculated root 2. Otherwise, you can calculate -1. -1 is the root of -1 square, 1 square. So you will get root 2. So here you will get 0.5 plus 0.5. Here in the numerator is root 2. So here you will get again 1 by root 2. And if you just divide, you will get 0.707. And similarly for C3 again, for D3 transpose R1 and D3. Okay. So again 1 into minus 0.5 plus -1 into 0.5. Okay. Mod divided by root 2. So here you will get minus 0.5 and minus 0.5 of root 2. Here you will get 1 minus 1, but it is in the mod. So overall you will get a positive value 1 by root 2, again 0.707. So now you can see that the both correlation values that we have got, these are the same values. Okay. So now you can choose any one. So D2 is the first one. So we will choose first D2. First check with the D2, then D3. Okay. So let's choose D2 first. So D2 is already, we know that value is -1 and 1. So now select set of atoms. I need to take another slide. So we have chosen the next atom is D2. So now the selected set of atom, our selected set of atoms are D1 and D2. Yeah, someone is asking. Yes. Okay, want to clarify one doubt in exams. Questions going to MCQ types or both written and MCQ? There will be a MCQ as well as comprehensive also. Comprehensive means that PCA type question, long questions, where you have to find out the principal components and directions, like based on the Fisher discriminator. And previously we have solved the many numerical questions as well. So you will get the comprehensive as well as MCQ. Okay. So our next selected set of atoms are atoms are that, let's say it is represented by A, and it is our first selected atom is D1 and our next selected atom is D2, right? So overall we can write it like this: from the selected atom 1 1, because D1 is 1 1 and D2 is minus 1 and 1. So from here you got the 1. Now we need to compute the final coefficients. So how we can compute the final coefficients? So for that we need to find out the coefficient vector, that is alpha, that is such that A alpha is equal to y. Okay, so here alpha we don't know. So A we know that 1 minus 1, 1 and 1. It is a 2D space, so we can take alpha 1, alpha 2, right? And here y already given in the question, that is 2, 3. So from here, now we can compute. So alpha 1 minus alpha 2 is equal to 2. And here alpha 1 plus alpha 2 is equal to 3. Right? Let's say it's equation 1 and equation 2. If you solve these two equations, if you add to these two equations, so you will get the value of alpha 1. Add these two equations. So here we will get 2 alpha 1 is equal to 5, right? And alpha 1 is equal to, you will get 2.5. Now put the alpha 1 value in equation 2. So you will get alpha 2 is equal to 3 minus 2.5 is equal to 0.5. You will get. So what is a OMP representation? So alpha 1, alpha 2 we have got, and our first two selected atoms, we know that D1 and D2. So the OMP representation is that is y is equal to, we can say that alpha 1 D1 plus alpha 2 D2, and y we know that 2, 3, and alpha 1 we have got 2.5 and D1 is 1, 1. Our alpha 2 is 0.5 and next selected atom is minus 1 and 1, that is T2. So from this is a just final answer, just check with the answers. So from here we will get the decision. Option A answer is 2, 3, 2.5, that is alpha 1 and alpha 2 0.5, first two selected atoms alpha 1 and D1 and D2. So from here option A is the correct answer for this question. Okay, so have you understand this question? Is it fine for you?
Okay, ma'am.
Okay. Okay, so I hope all of you have understand this question. So now moving to our next question. Okay, so our next question is, consider the given sample for two class problem. X1 is given, this is a class 1, and X2, this is the other data points related to class 2. Now compute both the within class and between class scatter matrices. So this is also a very lengthy question, and this type of question is MCQ can be, and can be this type of comprehensive as well. Okay, so can you please answer for this question at least, how to solve the within class scatter and between between class scatter matrix. Okay, so first two class samples are given, x1 and x2. In the x1, we have data points 42, 24, 23, 36, and 44. And in class 2, that is x2, data points are 9, 10, 6, 8, 9, 5, 8, 7, and 10, 8. So to compute the within class scatter matrix that is represented by SW, right? So SW is equal to S1 plus S2, where S1 is the scatter class in X1, scatter matrix, you can say that in X1, and it is a scatter matrix in X2. So for that also, and how we can compute the S1 and S2 as well. So S1 is calculated, that is the samples belonging to the class X1 and X minus mu I again, and X minus mu I transpose, that is basically mu 1. Okay, so this is for S1, and S2 also calculated the data points belonging to the class 2, and the again the same matrix mu I we can write it collectively, and X minus mu I transpose. Actually mu I, you will get the two mu I's for mu 1, class 1 and class 2. Okay, so for each, here for S1, the mean is for mu 1, mu I is mu 1, and for class 2, that is a mu 2. Okay, so first we need to compute S1 and S2, then we will add, and that is the our between class scattered matrix. Okay, so these are the data points you can see, or you can note down from here, because I will solve it in the next step. Okay, so first we will solve here the mu 1. So here these are the data points. So how we can calculate? So first point, sum of all the first points and the second points also. So 4 plus 2 plus 2 plus 3 plus 4 divided by here total data points are 5, right? And our next mu x, mu y, you can say that, comma, next 2 plus 4, the second data point, plus 3 plus 6 plus 4 divided by 5. So mu 1, if you add all these values, so you will get here 15 by 5, and here the next one is, you will get 19 by 5. Now further, just divide it, you will get 3.8. So this is a mean related to the first class 1, x1. Okay, so now our mean related to our next class, we will get here. So 9 plus 6 plus again 9 plus 8 plus 10 divided by 5. Similarly for the next data points, so just need to remove it from here. So 10 plus 8 plus 9, 10 plus 8 plus 5, sorry, 5 plus 7 plus 8 divided by 5. Just check with the values itself also. So here you will get 42 by 5 and here you will get 38 by 5. So if you further just divide it, you will get 8.4 and 7.6. This is the means or mu related to the second class, next class. Okay. So now we need to calculate the within scattered matrix first. So already we know that. So to compute x, to compute S1. So already we know that S1 is computed by so the data points related to the class 1, that is x minus mu1 and x minus mu1 transpose. So first we need to find out the x minus mu1 and here you can say that xi, that means all the data points related in the class 1. Okay. So here 5 data points are given. So first we need to calculate for the first 5 points this matrix. Then we will add all these matrix to find out the final S1. Okay. Or we can say, let's say we can also represent it X related to the class 1 MIs, that is related to MI represent this one X minus mu1 X minus mu1 transpose. Okay. So I'm just representing this matrix. This first one is to M1. Okay. So our first data point is here 4, 2, right? So that is X is 4, 2 and our mu1 is that we have calculated is 3, 3.8, right? So X minus mu1. So 4 minus 3 and 2 minus 3.8 and it's transpose as well. So 4 minus 3 and 2 minus 3.8. So it is 1 is in this way. So here you will get 4 minus 3 is 1 and 2 minus 3.8 you will get 1.8. Again here also 1 minus 1.8. So if you just multiply these two, so matrix you will get 1 into 1, 1 into 1 minus 1.8. So minus 1.8, again here minus 1.8 and 1.8 into 1.8 minus will be plus. So if you just multiply it 3.24 you will get. Similarly, we have to calculate all the data points that is related to class 1. So our next data point is 2, 4, next one is 2, 3, 3, 6 and 4, 4. For all these data points, we have to calculate this type of matrix and then we will add all these matrices to find out the S1. Okay, so I'm just giving the another name. So our next data point is 2, 4, right? So 2 minus 3, 4 minus 3.8. Here again 2 minus 3 and 4 minus 3.8. So here you will get minus 1 and 0.2. And here also minus 1, 0.2. So the matrix we will get 1 minus 0.2 minus just a minute minus 0.2 and here you will get 0.04. Okay, 0.2 into 0.2. Similarly for the M3 also. So can I write it directly? You can calculate it later. So just from each data point, you have
You can
to
write
subtract it. Okay, otherwise it will be very long. That question it will itself take the all the class. So here M3 we need to calculate. So next point is 2 and 3. So 3 minus 3.8. Here again 2 minus 3. 3 minus 3.8. So here you will get minus 1 and minus 0.8. here minus 1 minus 0.8. So if you just multiply, you will get the matrix 1, 0.8, 0.8 and 0.64. Similarly, for M next data point, you will get the value. I'm just directly writing the matrix. So 4.84 matrix you will get. Now for next data point, our next data point is 4, 4. Okay. So 4 minus 3, 4 minus 3.8. If you just calculate the values and matrix, so you will get 1, 0.2, 0.2 and 0.03. So already I have told you how to calculate these metrics, so that's why I have written it directly. Now to compute the S1, so already I have told you the summation of all the matrices. So MI, this one. So just I am removing it from here so that we can add all the matrices that we had calculated from the data points. Okay, so first data point is this one, next is this one, this one, this one, this one. So you have to add 1 plus 1 plus 1, 0, 1. Similarly, for the next minus 1.8, minus 0.2, 0.8, 0, 0.2. So S1 here, if you add all these data points, so in the S1, you will get 1, 1. So all the value is 1 here, 4. Here you will get minus 1. Here you will get again minus 1. And here you will get 8.8. So this is our S1. Now similarly, we need to calculate S2 also. Okay. That S2 is corresponding to the second class data set. So just how we have calculated the S1, similarly in the same way you have to calculate the S2 also. Okay, so compute S2, and S2 is related to the second data point. That means data point that is related to class 2. So that is x minus mu2 and x minus mu2 transpose. So in the second class the data points are, so x are that is given as 9, 10, 6, 8, 9, 10, 6, 8, 9, 5 and 8, 7, 10, 8, 8, 7, 10, 8. These are the data points related to the second class. Now to compute, let's say I am just doing is again for M1. This M1 is this one, that is MI. I am just representing the x minus mu I. So our x is 9, 10 for this one, or mu that for S2, mu2 that we have calculated, that is 8.4 and 7.6, right? So here you will get 9 minus 8.4 and 10 minus 7.6, and its transpose as well, 9 minus 8.4, 10 minus 7.6, right? So for this one you will get the values. If you just subtract 0.6, 2.4, and here again 0.6, 2.4. So if you just multiply these values, so matrix that you will get, that is 0.36, 1.44, again here 1.44, and 2.4 into 2.4 you will get 5.76. Okay. For M2, that is data point related the second data point in the class 2. Similarly, if you just do in the same way, you will get the matrix 5.76, 0 minus 0.96, minus 0.96, and 0.16. M3 related to the third data point, you will get a matrix of 0.36, minus 1.56, minus 1.56, and 6.76. M4 also you will get 0.16, 0.24, 0.24, and 0.36. M5, if you just same way, if you calculate, so you will get 2.56, 0.64, 0.64, and 0.16. Now we have to add all these matrices to find out the S2, final S2. So if you just add all these matrices, you will get here 9.2 minus 0.2 minus 0.2 and 13.2. Okay. And for SW, already we know that for SW, we have to add S1 plus S2. Okay. So for overall within class scatter matrix, we have to add S1 plus S2. That means this one and this one. So just I'm taking the another slide and adding all those things. So yes, W finally you will get the values 13.2 minus 1.2 minus 1.2 and 22. So within scatter matrix, this is our result. Now the between class scatter matrix need to find out between class scatter matrix, that is SB. What is the formula for between class? So this is mu1 minus mu2 multiplied by mu1 minus mu2 transpose. Okay. So first mu1 minus mu2 we need to find out. So mu1 mu2 we have already find out in the previous slide. So 3 minus 8.4 and next one is 3.8 minus 7.6. So mu1 minus mu2 you will get minus 5.4 and minus 3.8. Now to calculate SB, what we need to do? Minus 5.4 minus 3.8 and here minus 5.4 minus 3.8 because it is mu1 minus mu2 and mu1 minus mu2 transpose. So the matrix, if you just multiply these two, you will get here 29.16, 20.52, 20.52, and 14.44. So this is our within class scatter matrix. The values that we have got this one, and the between class scatter matrix SB. This is our between class scatter matrix. So if you match from the options, so you will get just SW is not matching with our calculated values, but here it is a wrong results has been presented because our SB is matching 29.16, 20.52, and 14.44. Okay, so here the values are not correct. So if you just match with this one, so you will get only SV value is matching, or that option A is the correct one. Otherwise, actually, it is a partially corrected question. Okay. So in the exam, you will get the correct question. Here the misprinted or something else happened because I have calculated in many other ways also. All the values I have checked, double cross checked it, but the value for SW doesn't match with this one answer, but SB is matching. That means the values is correct, but here this values are incorrect. Okay, so in that case, option A is the only correct because SB is matching with this one. Okay, so basically you just remember what is the procedure and how to calculate all these values. So this type of questions are very lengthy. So just you have to do all the calculations. Okay. So now in the next question, this is related to the previous question itself. So for the given data point given in question 6, compute the projection vector such that it provides maximum separability between data of the two classes following Fisher linear discrimination analysis, that is LDA. Now we need to find out the actually direction of the projection vector. So the projection vector W that maximizes the separability between the two classes. This is in the LDA. The formula already we know that is W is proportional to SW inverse mu1 minus mu2. That is the projection. W is the projection vector, that is W, that maximizes the separability between the two classes. Okay, so already SW we have calculated, so I am just taking the same value 13.21 minus 1.2 minus 1.2 and 22, that calculated values. So let's see whether it will come or not. 13.2 minus 1.2 minus 1.2 and 22. So first we need to calculate this one, that is inverse of SW. So how we can calculate? So already we know that 1 by determinant. This is a 2 cross 2 matrix. So directly determinant of SW. So directly just replace the A and D values and take a negative sign in this one, right? So 22, 1.2, 1.2, already it is a minus, so it will be the plus, and here 13.2. These values will be replaced. And determinant of SW, can we calculate the cross product of these two? So 13.2 into 22 minus 1.2 and 1.2. So if you just calculate this value, so you will get 288.96. Okay, so just put this one. So 1 by 288.96, 22, 1.2, 1.2 and 13.2. Okay, so overall SW inverse, if you just divide it inside the matrix, you will get 0.076, 0.0041. Yes, again here 0.0041, and here you will get 0.0457. So this is our SW matrix. Mu1 minus mu2 already we have calculated. Here mu1 minus mu2 is this value, minus 5.4 minus 3.8, right? So let me take one slide here. So W, that is SW inverse mu1 minus mu2. So this one we have calculated here. So here 0.076, 0.0041, 0.0041 and 0.0457. Okay, and mu1 minus 5.4 and minus 3.8 here. So just multiply these two matrices. So here you will get 0.076 into minus 5.4. If you multiply these two, you will get minus 0.4104. Here again this one 0. This one, so minus 0.01558, and here you will get 0.1558 minus 0.17366. Okay, so further you just add these values, so you will get minus 0.42598, and here you will get minus 0.18924. Okay, so that value we have got a raw vector. Now we have to normalize it. Okay, so normalize this W. So the projection vector is typically given as a unit vector. So to normalize W, what we are doing, root square of minus 0.42598 square plus minus 0.18924 square. So if you just calculate, so you will get 0.217272, and here you will get 0.466. Okay, so the normalized value W norm, you will get 1 divided by 0.466 minus 0.42598 and minus 0.18924. So if you just divide inside, you will get minus 0.9138, and here you will get 0.4059, and we can write it in the second 0.91, or you can take the minus out also, 0.40. Okay, so this is our normalized W. So from the answers, if you match, so this one is the closest, 0.90 and 0.41. Okay, here 0.91 we are getting and 0.4059, so 0.41 approximately. Okay, so option B is the best matching from the answers that we have calculated from here. Okay, so have you understand this question? Can we move to our next question? Actually, we are running out of time.
Yes, ma'am.
Also.
Yes, ma'am.
Okay, so I hope all of you have understand this question. Now moving to our next question. Now next questions are related to theoretically only. So question is, which of the following are true with respect to KSPD? Option A, it is a dictionary learning algorithm for sparse representation. Option B, it is a generalization of K means clustering algorithm. Option C, it works on the updating dictionary atom until convergence. Or option D, all of above, all the above. So any one of you have any idea which option can be a correct one? Which of the following are true with respect to KSVD? Anyone? At least try
All
to
the above,
answer.
ma'am.
Okay, all the above. Okay, let's see the detailed solution I have added here. So KSVD is key singular value decomposition. Yeah, D correct. Sorry. So is an algorithm for dictionary learning that is widely used in the sparse coding as well as signal and image processing. So that learn to over complete dictionary such that signals can be represented as a sparse linear combinations from the dictionary atoms. So it alternates between the sparse coding step as well as and a dictionary update system in the sparse coding step that represents signal with the current dictionary. And in the dictionary update system, what we are doing? Refine dictionary atom with SPD until convergence. So our options are given. It is a dictionary learning algorithm for sparse representation. So that is true. So that's exactly what SKSPD is designed for, learning a dictionary that enables sparse representation. And it next option is it is a generalization of the k-means clustering algorithm. So yeah, this is a generalization from the k-means clustering algorithm that has been a special case of the KSPD where each signal is represented using the only one atom, and KSPD generalizes this is allow a sparse linear combination of the multiple atoms. Our next option is it works on the updating dictionary atoms until convergence. So yeah, our next step is in the KSPD dictionary update system. So in that case, in each iteration, dictionary atoms are updated one by one using SVD on the residual error matrix. So already we have solved one question on that. So that we have seen how it is updated. So this continue until convergence or stopping criteria is reached. So since all the options A, B and C are correct, so correct answer is the all of above. All the above, you can say that. So option D is the correct answer for this question. This one. Now our next question is which of the following sequence of the various stages in KSPD is correct? So option A is initialization of the dictionary, sparse coding and dictionary update. Option B is sparse coding, dictionary update and initialization of dictionary. Option C, dictionary update, sparse coding and initialization of the dictionary. Option D, initialization of the dictionary, dictionary update and sparse coding. So can you just tell which option can be correct? Already we have seen what is a process and what is the sequence for the KSPD. So what is the sequence?
Option D, ma'am.
Okay, option D. So initialization of the dictionary, dictionary update and sparse coding. Okay, okay, so let's see on the answer. Actually, the initialization of the dictionary, then sparse coding, and then dictionary update in the last. Basically divided in the two main list step in the previously we have seen the sparse coding step and dictionary. So before that we have to initialize that one, then sparse coding step, then dictionary update. So here they in that previous one we have not written that one. So first option E is the correct. First initialization of the dictionary, then sparse coding, then we need to move on dictionary update. Dictionary update is the last sequence. Okay, so KSVD is an iterative, that is iterative algorithm that starts with the initialization. Yes, that is initialization, and then alternate between the two main steps, sparse coding and dictionary update. So correct sequence will be the initialization of dictionary, sparse coding and dictionary update. So from there, the correct option is A. Okay? Option A is the correct answer. Just don't confuse about the initialized dictionary update and sparse coding. So first is sparse coding and next one is the dictionary update. Okay. So now moving to our next question. This is again related to this one. The statement that KSPD is generalization of the K-means is true because option A, both are dimensionality reduction techniques. Option B, KSPD can be viewed as a K-means where a data point is represented by a single atom with a non-zero coefficient. Option C, KSVD can be viewed as a K-means where a data point is represented by a sparse linear combination of multiple atoms. Or option D, both algorithms requires an initial random guess for the cluster center or dictionary atom. So here the statement that KSPD is a generalization of K means is true. Which option can be a correct one? Okay, so let's move to the detailed solution here. So your detailed solution is given. The in K-mean, a data point Y is represented by its single closest cluster center, that is a DK, where coefficient is 1. In KSPT, the same data point Y is represented by a linear combination, that is Xi and Di. That means different data point and their closest cluster center, Di, with the constant that coefficient vector k is sparse, mostly xi are 0. So when sparsity level is 1, KSV reduces to the k-means clustering objective, that is a representation by a single atom. So thus KSPD is generalization allowed for the sparse combination. The correct answer is option C. That means KSPD can be viewed as a k-means where the data point is represented by a sparse linear combination of the multiple atoms. Okay, so option C is the correct answer for this question. Now moving to our next question. Our next question is the sparse coding step in KSVD involves finding the coefficient matrix X that minimizes. Option A, the L1 norm of the dictionary D. Option B, the total scatter ST of the dataset, that is reconstruction error, that is Y minus Bx mod of F square subjected to the sparsity constraint on X, or option D, the mutual coherence between the dictionary atoms. Which option can be a correct one here? Anyone? Try to answer at least. Okay, so let's see the detailed solution. So detailed solution is the sparse coding phase that is using in OMP, that is orthogonal matching pursuit, fixes the dictionary D and solve for the coefficient matrix X. Okay. The objective is to minimize the covariance norm square of the reconstruction error, that is y minus dx, so which measures how accurately the data point y can be reconstructed while simultaneously imposing the sparsity constraint on the coefficient vector x that typically minimizes the L0 or L1 norms. The correct answer here is also C. The reconstruction error y minus dx mod of f square subject to the sparsity constant on x. Okay. So our next question is again related to PCA. PCA can be viewed as a finding a lower dimensional subspace W such that when the data is projected and then reconstructed back into a original space, the total reconstruction error is minimized. The error is measured as the sum of squared distances between the original data points and their projections. The minimum error is related to option A, the largest eigenvalues lambda 1, the sum of discarded eigenvalues, option C, the sum of retained eigenvalues, or option D, the determinant of the covariance matrix. Which option is correct? At least try to answer for this question. This is a PCA related question. PCA can be viewed as a finding of the lower dimensional subspace W such that when the data is projected and then reconstructed back into the original space, the total reconstruction error is minimized. The error is measured as the sum of square distances between the original data point and their projection. So the minimum error is related to which one? Okay, so this is okay. Let's see. So let's see in that
B,
case.
ma'am.
Okay, okay. Let's see. Yeah, correct answer is V. So if PC retains K components corresponding to the largest eigenvalues, that is lambda 1 to lambda k, and the discard M components corresponding to the eigenvalues, that is lambda k plus 1 to k plus n, the total squared reconstruction error, that is not the energy not captured, is exactly equal to the sum of the discarded eigenvalues, that is I belongs to k plus 1 to k plus m to lambda is. Okay, so this one, total discarded eigenvalues. So correct answer is B, the sum of the discarded eigenvalues, not a retained eigenvalues. Okay, okay. So now our next question is, in the context of the OMP, the term orthogonal refers to the fact that option A, the selected dictionary atoms must be mutually orthogonal. Option B, the coefficient vector x is guaranteed to be orthogonal to the dictionary D. Option C, the newly calculated residual error is always orthogonal to the subspace spanned by a previously selected atom. Or option D, the input vector y must be normalized to be the orthogonal to the residual. So in the context of OMP, the term orthogonal refers to the fact that the orthogonal, which is the orthogonal terms related what it refers. Can you tell? Okay, so first moving to the solutions because I have so many questions now. So at each step of the OMP, after selecting a new atom, the algorithm perform a least square projection of the original signal onto the current span of the all selected atom, and the residuals is defined as the difference between the signal and this best projection. So by reconstruction, the least squared error vector, that is the residuals, must be orthogonal to the subspace from which the projection was calculated. So correct answer is C. The newly calculated residual vector is always orthogonal to the subspace spanned by the previously selected atom. Okay. So now our next question is, which transformation of the original data will not change the direction of the principal components derived by standard PCA? Option A, nonlinear transformation, that is x related to the x square. B, rotation of the coordinate system, or option C, rescaling only one feature, that is multiplying one column by 10, or option D, applying a constant offset to the entire data set.
Option C, ma'am.
Okay, rescaling only one feature. Okay, so which transformation of the given data will not change the direction of the principal component derived by PC? Okay, so the standard PC is performed on the centered data. Already we know that that is mean data. A and C will change the covariance matrix dramatically, thus changing the principal component, and option B changes the absolute coordinates, but not a covariance is calculated related to the mean. So the covariance rotates along with the data, preserving the relationship of the component to the data structure. So the component themselves will also rotate. Okay. And option D, applying a constant offset is removed by the mean subtraction step, that is x minus mu plus c or x minus mu minus c plus c. X minus mu you will get only. Since the relative position of the data points remains unchanged, so the covariance matrix remains identical in that case. So correct option is option D, applying a constant offset to the entire data. Okay, so this transformation will not change the direction of the principal components derived by the PC. So applying a constant object of through the entire data. Okay, so this is an important question can be from your exam point of view. So this type of question basically they will ask. That's just application based or some conceptual questions. Okay, so now next question is in LDA the total scatter matrix that is ST relates to the within class SW and between class scatter matrix by which equation? So in LDA, the total ST and SW, SB scatter matrix is related to by which equation? Option A, ST is equal to SB minus SW. Option B, SW divided by SB, or ST is equal to SW plus SB, or ST is equal to SW into SB. So which in LDA, which equation related to within class and between the class scatter matrix? Anyone? At least answer for this question. Okay, Swati is giving answer C. Okay, yeah. So let's see answer. Answer C is the correct answer. Swati. So the total variance or scatter of the data can be decomposed into the variance within class and between class matrix. So this is expressed by additive property of the scatter matrix, that is total matrix is equal to SW and SB. So this decomposition is essential to the both PCA and LDA. Yeah, correct answer is option C is the correct answer. ST is equal to SW plus SB. Okay. So yeah, now our next question is a PCA analysis yields the following eigenvalues for a four-dimensional data set. So four-dimensional. So the eigenvalues is that lambda 1 is equal to 8, lambda 2 is equal to 4, lambda 3 is 2, lambda 4 is 1. Now they are saying that if you decide to reduce the dimensionality by 2, what percentage of the total variance is retained? So how to solve this question? Here four-dimensional data set is given. The eigenvalues of the four-dimensional data is given. Now they are asking if you reduce the dimensionality to 2, so what percentage of the total variance is retained? So first we need to calculate here the total eigenvalues, that means sum of all the lambdas. Actually my pen is not working, so I will show you the solution here. And if we choose the two dimensional, so that the highest two eigenvalues dimension. So here are detailed solution I have given. First we need to calculate the total variance. So total variance is the sum of all eigenvalues, right? So 8 plus 4 plus 2 plus 1, so it will be 15. Now to calculate the retained variance. So the retained variance is the sum of the eigenvalues corresponding to the kept component, the largest two. So we are retaining the lambda 1 and lambda 2. The values related to 8 plus 4, that is total. So to calculate the percentage, so retained percentage is calculated by the lambda retained divided by lambda total multiplied by 100. So 12 by 15 into 100, so 0.8, that is 80%. Okay, so just take option B is matching. So option B is the correct answer for this question. So the 80% of the total variance is retained if we choose the two dimensions, that is the highest eigenvalues. Okay. So our next question is again little bit numerical. So a 10-dimensional data set contains four distinct classes. That means we have four different classes in the 10-dimensional data set. What is rank of the between class scatter matrix SB in this LDA problem? So how we can solve this question? Okay. So the detailed solution already I have added here. So the rank of the between class scatter matrix SB is at most C minus 1. Okay, where C is the number of classes. So here we have how many classes? 10. C is equal to 10. No, 4 classes is there, right? 10 dimensional and 4 distinct classes. C is equal to 4. And our dimension D is equal to 10. So here rank SV minimum of 10, 4 minus 3. So here 10 minus, so 3 is the minimum. So this means LDA can be fixed, find a minimum 3 useful discriminant features. So correct option is option B. So the rank of the between class scatter matrix in the LDA problem is 3. Option B is the correct answer for this question. Okay. So now our next question is a signal y is represented by y is equal to dx, where the coefficient vector x is given 0.50 minus 1.20 3.2. What is the sparsity label, that is k, of this representation? What is the sparsity label? So let's see the solution. So the sparsity label k is defined by the number of non-zero entries in the coefficient vector x. So let's see. In the x, how many non-zero vectors are there? There are three, that is 0.5 minus 1.2 and 3.1, right? So the sparsity, so the non-zero entries are 0.5 minus 1.2 and 3.1. So there are three non-zero entries. So sparsity label is k is equal to 3. So option C is the correct answer for this question. The sparsity label is 3. Okay. Now moving to our next question. Given a vector y is equal to 1, 5 and normalized dictionary D is D1 and D2, where D1 is 0, 1 and D2 is given as 1, 0. Which atom is selected first by OMP? A D1, option B D2, both C D1 and D2 or neither?
Option A.
Yeah, option A is the correct. Already we have seen that. So which one is closest, or the is first option will be given already, first priority will be given to the first atom, that is D1. Okay, so option A is the definitely a correct answer. But let's see. So in the detailed solution, so OMP selects the atom with the maximum absolute correlation, that is inner product with the current signal residuals. Okay, so correlation with D1. So already we have seen D1 transpose Y, so 0, 1, 1. So 0, 1 plus 1, so you will get 5. Correlation with D2, here you are getting the 1 only. So since 5 is greater than 1, so first selected atom will be the D1. Okay, option A. Option A is the correct answer for this question. Now our next and last question is Fisher linear discriminant analysis, that is LDA, finds a projection vector W that maximizes which of the following ratios? Option A, W transpose STW divided by W transpose SW W, that is ST, where ST is the total scatter, and option B, W transpose SB, that is between class scatter matrix W, and divided by W transpose SW, that is within class scatter W. Option C is W transpose SW W and divided by W transpose SB W. Option D is lambda 1 divided by lambda 2, that is the ratio of the largest to the kth smallest eigenvalues. So from the LDA, which of the following projection vector W that maximizes the ratio? Which option is correct? So you must be, if you have studied about the Fisher linear discriminator, you must be seeing this relation. Any idea for this question? Which option can be a correct one? Okay, so let's see the solution here first. So LDA seeks a projection where classes are spread out from each other and compacted internally. So this is achieved by maximizing the Frisell criteria, which is the ratio of the projected between class variance to the projected within class matrix SB divided by SW. Maximizing the ratio ensure maximum class separation after projection. So correct answer is B. That is SB divided by SW. W transpose SB, W divided by W transpose SW, W. That is between class, scattered divided by within class. Correct answer is B. Okay. So now questions that have been completed. If you have any doubt, you can ask. Otherwise, we can close this session. So thank you everyone. Thank you for joining this session. Now, if you have any doubt, you can ask.
Thank you so much, ma'am.
Yeah. Thank you. Thank you everyone. Thank you for
Presentation.
joining this session.
Madam, my
Now,
daughter wants to say good night to you. Thank you and good night.
okay. Good night. Good night.
Good night, ma'am.
Good night. Okay. So now you can leave the session if you don't have any doubt. Good night. Good night.
Okay, ma'am. Thank you. Himanshu
Thank you.
also. Younger one. Good night. Say good night to ma'am.
Good night. Good night.
Thank you, ma'am.
Yeah. Thank you. Thank you. Okay. So any doubt? Okay. Okay. So thank you everyone. Thank you for joining this session.